Okay. Yeah, I'm Skylar Tibbits, faculty here, Department of Architecture. Lab is across the hall, as you heard. Outside of MIT, I run the 3D Printing Additive Manufacturing Journal, and I've been doing that for over a decade. And when I came in, I added the plus. So I was interested in what is the next generation of 3D printing? What are other forms of additive manufacturing? Not only printing itself, but knitting, jamming, growing, all these other things. So to me, that's really interesting because it's not just designers and artists, but it's engineers and computer scientists and physicists and whoever else. Um, and then I'm guessing everyone here knows about the new building that we're going to move into on the Met building on Mass Ave. And we're all sitting in Morningside Academy for Design. Have you had John here or any of the morning? Have people talked about MAD?
No, but people
Okay.
are planning to go.
People know about MAD. Okay. Anyway, so I'm one of the faculty chairs and I'm going to give it to. Okay. Okay. Well, Banaz and I are both MAD faculty, and Dave Wallace is the third one. But anyway, MAD was started 3 years ago, I think. Gerald Chan gave a gift to MIT to amplify design across campus, and the idea is to have design through education, design through research, design through faculty, staff, students, all different disciplines. There's events, there's lots of different opportunities. There's fellowships. Anyway, so I'm part of that physically because this is Mad Space, but also I help lead the education part and I'm faculty. And then what I'm going to talk about today is the lab. So this is not what the lab looks like anymore. It's a lot crazier, messier over there. You can go peek your head in. But anyway, we've been here for a number of years. Originally, it was the International Design Center through Singapore. Now it turned into MAD. And we have these three different scales of research that we look at. So materials, fabrication, and construction. But all of it is trying to figure out how do we build in a smarter way? How do we build smarter systems? How do we do this with less and less and less? So building more elegant solutions that have more intelligence. And how do we do that through material intelligence rather than traditional computer, robotic mechanisms or computer as intelligence? Can we take advantage of the way that all of us are built out of materials, not built out of robots? And can we find ways to connect materials with environments? So that's like the broad ethos, and we do that through three different, oh, you see the camera, sorry.
No, it's just I want to move this if possible because it's
Well, it's funny because I was not seeing it on your screen, but seeing it on here. Yeah,
it's
maybe we
difficult.
can
I
hide
don't
the
see your
visuals some.
um
Yeah, there you go. Let's just do it like that.
and this
Oh, there
one.
we go. Yeah, hide controls at the bottom.
I just don't know where's your mouse.
I don't know, it doesn't show it to you.
Okay.
Anyway,
Well, it's okay.
it's fine.
Sorry.
It's good enough. Okay. Um, I'll start with the materials part. We call that programmable materials. The idea is that you take physical materials, they change shape, they change property. We want to embed in agency, intelligence, sensing, logic, like all the things that we traditionally have in robotics, and we want to do that through standard materials. And there's a whole category of material called smart materials, and in a way, we're saying everything is a smart material. So wood, metal, plastic, foam, rubber, textiles, like all of those things can be smart materials. It's not like a special class of materials. They're not these magical materials that are expensive and complicated and need to be invented, but we look at everyday materials around us and try to amplify their agency. And a lot of this started in 2012 on a project called 4D printing. Before that, when I came to MIT as a student, well, even before that, I studied architecture. Then I got into writing code and digital fabrication. And then I came to MIT. I was under Neil Gershenfeld's lab, the Center for Bits and Atoms, and I was under a DARPA programmable matter grant. So that was 2008. And we were doing programmable matter. And at that time, it meant robots, like small robots, big robots, build everything, build the world out of robots. And actually, Big Hero 6, has everyone seen that movie? At the end of it, they credit the Center for Bits and Atoms, and they were there, the like film crew, director people were there. Um, and I was building the macrobot and the decibot, and in the movie they put the microbots, and then we were building soft robotics. Like a lot of that stuff came from the time that we were working on this DARPA programmable matter grant. But if you see in that movie, like everything is robots, and that was kind of the vision of programmable matter almost 2 decades ago. But I sort of got critical of that, and I was thinking, like, as an architect, we don't want to build buildings out of robots. maybe Sergio does, but we all don't want to do that. No, just kidding. But it is challenging. Like every brick being a robot is expensive, it's failure prone, it's energy intensive. It's not necessarily the best for scaling, either physically scaling bigger and bigger and bigger, or scaling like tons and tons of parts. So I was trying to figure out, well, how do we do this without robots? And this project happened because of Flower. I was at Flower and there was a person in front of me in line that had a Stratasys shirt on. And I was like, Stratasys, like the 3D printers. And then I just asked her, can't we print robots? Like, isn't there a way that I could print something that would walk off the machine? And that like started the whole collaboration. And then she's like, well, let me put you in touch with our material science group. And then I started talking to them about it. And they said, we have this weird material that it expands a lot. We can't sell it. No one wants it, but maybe we could use it for you. And so that started this project. And the vision was just like, could we print something that would become alive, that would have logic, sensing, actuation all embedded in it? So in the joint is this hydrogel, this magical material that was useless to them, but it would expand when it met water, and that would cause the structure to fold. And depending on how much material we put and what geometry, it would change into different shapes. So we printed this line and then it folds into a cube, and we print this line and then it folds into the letters MIT. In the beginning, we only know how to do 90 degrees, and then we got to other precise angles. And then we got into these like curved crease origami structures with Eric and Marty Domain. And then we got into linear expansion and contraction. So we were doing all these different mechanisms like folding, curling, stretching. And each one was just trying, it was a demonstration of like, would it be possible to do this kind of transformation? We did a much bigger one, which was a 50-foot structure underwater in the Olympic swimming pool. Anyway, there was a lot of research around that. And then I presented it at TED, and I was basically saying like, this is a way that we can make active materials for everything. And then a lot of companies started coming to us and saying like, can we do it in cars and shoes and planes and whatever it is? And that at that point, the vision to me was not about printing anymore. It was like, can we just do this in any manufacturing process with any materials? And that's why now I talk about it as programmable materials, not as 4D printing, because printing is one way, but knitting is another way, and injecting is another way, and laminating is another way, and there's a million other ways. Um, and so for almost 2 decades, we've worked with lots of researchers and companies and many different people. And this is printed wood that folds based on moisture, or carbon fiber that transforms with temperature. These are thin films. We put it in our book, Active Matter, and it opens and closes with temperature. So with Google, we did this whole shading system where it's basically stickers for buildings. You put them on the outside of the building. It opens and closes with sunlight, and that stops solar heat gain and glare. We did an exhibit at the Cooper Hewitt. Then we started doing auxetic structures, and I think some similar projects you were just showing. Then we started putting it on the body and thinking that this could create breathable clothing and apparel. And at that point, we applied to AFOA, which is Advanced Functional Fabrics of America. And under the Obama administration, there was a big push for manufacturing to come back to the US. And at that time, the idea was let's be more innovative than anyone in the world. And now the idea is let's force everyone to come back. But anyway, we can say that the previous idea I think was better. Anyway, so they would fund innovation in manufacturing. And so there was a 3D printing one, a composites one, a textiles one. There was all these like innovation centers around the country. And MIT won the grant for the textile one. And so Yoel Fink was the head of that. And they moved 2 blocks away. And we applied at the very beginning for a grant, and we said, we've done 4D printing, we've done composites, we've done lamination and auxetics, fund us and we'll figure out how to do this in textiles. And so we got that grant, and now, I don't know how many years, like 10 to 15 years later, it's 3/4 of our work is in textile. So we did textiles that sense pH and change with moisture, and then textiles that transform based on temperature. And 3 main applications started showing up. The first one is tailoring, which is what this is showing. So think of like ski boots, shin guards, mouth guards, these products that morph to the body. Clothing is a prime example of where we might want personalization, but it's really hard to do that. So what we were proposing, or still are proposing, is that we would make one garment and then we could morph it to fit the perfect shape. So we can get perfect sizing or styling, and you can transform, in this case, a dress. Like we worked with Ministry of Supply on their Newberry store. We put 20 dresses in the store, and the robot is going around heating the dress, and then it morphs to create the perfect size or shape or pattern. So it's sort of like dress DJ. We had 20 dresses, and then we played different patterns. We had like pleating, and we had bodycon and A-line, like all these different dress shapes. And so the vision is that they would only have one SKU. So normally the two problems with inventory for apparel companies is they have way too much product and they miss the mark on style or sizing. And so, then there's a lot of waste and then there's a lot of revenue lost. So it's a huge issue in the apparel footwear industry. And so anyway, the idea is they would have only one product, but they could morph it to a whole range of sizes. And so we've done masks during COVID. We did dresses with Ministry of Supply. We did sports bras with Decathlon, working on shoes. So there's like a whole range. The second application is climate adaptive textiles. So textiles that continuously morph. And the way to do that is we had to make custom fiber. So each one of these is a custom fiber that we had made. They have different materials, colors, and cross sections. And then we knit them into structures and they morph in different ways. And so those structures, some of them bulk, some of them create pores, some of them change thickness. The textiles have different mechanical behaviors. So the material property is what responds to the temperature and it does it reversibly. And then the knit structure is like the mechanism. So how does it stretch, expand, contract, bulk, whatever the like physical mechanism is. And then the zone is the third part. So you can knit the garment with different functions in different zones. So under the arms might need something different than the body, back panel, or the shoulders or whatever. And so we can have different zones that have different behaviors. And you can get things like porosity change or thickness change. So the vision of this one is that you would have clothing that adapts to either how your body is changing temperature or more likely is how the environment is changing because your body temperature actually is very minimal to change. But the exterior environment in this case, what we focused on was you go indoors when it's winter, it's super cold outside and it'll be super hot inside, or in the summer, it's air conditioned, cool inside and super hot outside. You have like 10, 20, 30 degrees of temperature change in 30 seconds. So you have a huge swing. But if you're ski touring, it might be the same kind of thing. You have these massive temperature swings, either because of internal or external. So we're trying to create apparel that basically adapts to you or your environment. With Arc'teryx, we did a jacket where all the insulation is knit and the insulation bulks with temperature change, so you can adapt for ski touring. And then the third category is multifunctional knit structures. So this is a spacesuit project we did with Dave and Newman and Hugh Herr and Svetlana and a few others on campus. And so there's the normal spacesuits where the astronauts are falling and they're big, bulky, like inflatable suits. There's another kind of spacesuit called a mechanical counterpressure suit, and that's usually like originally it was high altitude pilots would use that, but it's physically squeezing the body. So like mechanically creating compression instead of air pressure. There's a lot of advantages of that because it's easier to put on and off. It's safer. Like if you pop it, you might break a blood vessel, but you don't die. In the air pressurized suits, if you pop it, you die. So there's, some significant advantages, but it's really hard to make that. Like if you take a standard textile and you wrap it around your arm, the compression is going to be different all around your arm because the shape of the arm is different and the movement of the arm is different. So anyway, what we showed is that you can go from a 3D scan of the astronaut's arm into a custom knit structure that gives you exactly the right amount of compression where you need it. You can embed sensors to then tell you what kind of compression or tell you how you're moving. On the outside, you can have radiation debris shielding. You can do all sorts of different like mechanical and material functions. And so this is a way that the knitting becomes like an assembler. We can assemble all these different functions into one garment instead of having like traditional cut and sew and layering. Like we went to David Clark Company, who's made a lot of the spacesuits. They're like 30 minutes away. And it's people sitting at sewing machines with like hundreds or thousands of parts sewing these spacesuits together. So in this way, you can knit the thing and it can have all these functional properties. So that was with Deva. There's more to the textiles work, but that kind of gives you a quick overview of the three different categories: the tailoring, adaptive textiles, and multifunctional systems. So then in the fabrication work, you can see how much our work is really aligned with the fabrication processes, like whether that's 4D printing or whether that's knitting. It's really working with materials and how they're fabricated together in order to create different behaviors. At some point, we started to realize that we needed to build our own. A lot of that came from, it says rapid liquid printing about that, but a lot of that came from frustrations from the printing companies where they would sell you these machines, but they're kind of black box and you couldn't hack them or manipulate them. Otherwise, you would void the warranty. And so we didn't feel like we had the freedom. So we developed this printing process called rapid liquid printing. Originally, it was with Steelcase, the furniture company, and we print it inside this vat of gel. The gel eliminates gravity, and that allows us to print freeform, like 3D calligraphy. So we don't have to print support materials. We can change pressure or speed on the fly, and that changes the line weight. We don't have to wait for it to cure locally. So the reasons that printing is slow is you're wasting a lot of time and material for supports, and you have to cure it step by step. In ours, we just print and everything is curing chemically. So the printing is separated from the curing. And we don't have to like flash it with UV or anything. So that's why we can go fast. We can make soft materials. So these ones stretch 1,000%. They make soft robotics with multi-chambers. We can do like inflatables and all sorts of different things that you traditionally couldn't print. And then we can go big. So this is a car seat cushion. It's about 1.5 meters by 1 meter or something like that. So it's quite large. And the largest machine that we had was a 5 foot by 10 foot machine. So you can really get big things, soft things, fast things. This one, the vision was that the cushion could morph around your body. It could change stiffness for comfort. It could change like crash protection or lumbar support or massage features, like all these different functions that car seats have today. Could we embed them into one, basically Baymax for your car, like one soft robotic system in your car that would do everything you need, but all of the intelligence is built into just like how the chambers are printed and how you can get things to morph. Then we've done lots of projects through the lab. We did all these home goods. A lot of this was with product designer Christoph Gubran, who taught in the design minor major here. He's teaching me with a studio with me right now, a Luma studio. We did footwear, we did automotive and all these things. And then we spun this out as a company. So they're in Charlestown. We have a print for service part where we print parts for any footwear, automotive, prosthetic, medical device. And then there's a machine. So we sell the machines as well. So that's spun out. And then in the lab, we started focusing on high temperature materials. So instead of printing in the gel, which is made out of water, we print inside of glass beads. So very, very, very fine glass beads. And we print with molten aluminum. So it's like 6, 7, 800 Celsius. We melt it in a crucible. We extrude it out. It's flowing and molten. And then we draw very, very fast. And so this one's even faster than the previous. Like this one is under a minute to print a meter scale object, whereas the previous one is like tens of minutes. So 10, 20, 30, usually under an hour. This one is under a minute. So it's very, very fast. The vision here is that most metal printing, we print high precision, high value parts in automotive, Formula One, aviation. And ours is the opposite. Like look at the table, the chairs, the components around you. Like none of those need micron resolution. They need to be big, fast, and cheap. So we're going that direction. Like how do we print structural large scale parts as cheap and fast as possible? And then it's fully recyclable. Aluminum is one of the most amazing materials for recyclability. So like all of these chairs are made out of aluminum. It's supposed to last 150 years. We collaborated with Emeco on that project, coincidentally, who make these chairs. But they, that product, even though it takes a lot of time to build it, it's all fully manual. It's made out of flat sheets. It lasts over 150 years, probably lasts far longer than that. We can use it as a sawhorse and a workhorse, and you can like probably park a car on it. The thing's indestructible, but it's also fully recyclable, which is crazy. So it's kind of an amazing material in that way. Zane Carson did his master's thesis on this. He's now at ETH doing a PhD, but he showed that we could do chairs. So the structure of the chair would be printed in under 2 minutes. In this case, the table would be under 3 minutes. He showed that the print would have the same mechanical properties as a sand cast, so we can get structural parts. The resolution is not great, so it's like fast, cheap, big, poor resolution. But what he was arguing is that you can do surface machine and you can get all the surface, bore holes, precision, threads, surface finish that you want just in a post machining process, and you get basically near net shape really fast. Anyway, so that one's still research. And then I'll go to the largest category, and I'll show you a couple different projects there. So we've done a lot of work on a phenomenon called granular jamming. So granular jamming is where you have particles and they get stuck mechanically and they act like a solid. But when they have room to move around, they act like a liquid. So this is like at the beach when you jump on the sand and it's like hard, or if you hit the sand, it's hard. But when you play with the sand, it's soft. The particles get stuck and they're a solid. There's often in the soft robotics community, there's a bladder with coffee grinds in it. You pull a vacuum, it feels like a brick. You put air in, it feels soft. So they use that for like a robot gripper. We worked with Gramazio Kohler's group on a project called Rock Print, where we used rocks and string. This is for the Chicago Architecture Biennial. And there's a big yellow bounding box, and there's a robot spitting out string. So rock string, rock string, rock string, over and over and over again. The robot's printing string layer by layer. We're pouring in rocks. And then when we remove the bounding box, all the rocks fall away that didn't have string, and only where there's string does it jam. So the reason this works, there's no membrane, no vacuum, but the string takes tension, the rocks take compression, so it acts solid. There's nowhere for it to go. And then at the end of the exhibition, we can wind it up and the whole thing can disintegrate and then be reused. So the benefit here is it's like concrete in that you can pour it like a liquid, but there's no cure time. Normally concrete takes 30 days to cure, makes a huge mess. Farida is our resident jamming expert. She's been working on a whole project with DARPA on jamming for a couple of years. But anyway, so that one, it's instantly solid. You can pour it like a liquid, becomes load bearing, but then it's fully reversible. You can do it over and over and over again. And we've done a bunch of projects around that. And then let's see if I can get this to play. Yes. Okay. And then another kind of the opposite thing as jamming is granular convection. So this is like the Brazil nut effect, or when you have a box of cereal and you shake it, and the more you shake it, the more it separates. So it's the opposite. It doesn't actually mix, which is what you would think. So we use this phenomenon with the project with Adidas, where we're basically trying to create a midsole that adapts and evolves to how you need the support and comfort over time. So we have three different particle types. There's a really soft, big bead. There's a kind of medium soft bead, and then there's a really stiff recycled tire bead. And over time, the large particles rise to the top, creating cushion, and then the stiffer particles go to the outsole where it needs the support. So what we did is we had the robot run a marathon on it. So it did 40,000 heel toe strikes on top of this, and you'll see the soft particles rise just where the heel toe strikes are. So you basically get cushion right where you need it in the heel toe as you're running. And then everyone, as they're running or walking, their midsole becomes unique to themselves. So you don't have standard midsole, standard shoes, even though they're manufactured all the same way. Eventually, all of our shoes would be different. And so that's a way that the product could evolve over time. Okay, and then the last category, the name of the lab is called Self-Assembly Lab because we're interested in this phenomenon where disordered parts build ordered structures without humans or robots. So all of us are self-assembled, the planet is self-assembled, like all natural systems use self-assembly or self-organizing systems. And it became interesting to me because if you look at every scale, I mean, this is called design across scales. If you look at the smallest scales all the way up to the largest scales, self-assembly is the phenomenon of how things are designed, but also how things are built. And if you look at human scale, if you look at like construction, manufacturing, it's all top down. So it's like, I have an idea, I send my idea to robots and machines, and they execute my idea. But at every other scale, it's all bottom up. So design and construction emerge from the interaction between parts and their environment. And so that became like a really interesting lifelong question about why don't we use that as humans? Why don't we use self-organizing systems? We've done a lot of experiments. This one, the particles float around underwater and they make this chair. So they're tumbling around. All the parts are unique. They have to find the right place. This one was in the courtyard out here. All the parts had helium in them. They're weather balloons and they have Velcro nodes and they move around, and we filmed it over a weekend, and they make all these different structures like beams and cubes and different kind of lattice structures. And we did small ones, we did big, this is the biggest one we did. We did floating ones, underwater ones, tumblers, all different geometries. Some are self-similar, some are unique. Everything it was kind of like the 4D printing days where everything was just trying to ask a question. Is it possible to do floating ones? Can we use Velcro as the connection? Can we change the geometry to make an arbitrary shape like a chair? Can we make self-similar shapes? Like there were all these somewhere between art and science trying to just ask more basic questions about what's possible for self-assembly. But then about a decade ago, we got invited to go to the Maldives, and it's a kind of random event again. I was presenting at Pecco's sports conference on campus about the textiles, and a woman from Sri Lanka came to the lab, and she said, "My husband's Maldivian. Why don't you come to the Maldives and apply some of the self-assembly work?" Because she saw these things under the water in the tanks. And we're like, yeah, let's go to the Maldives and see what's possible about. I mean, that sounds cool. Let's go on a trip. And then when we got there, they took us out to this sandbar. And this sandbar, they said, showed up in a month. Like out of nowhere, sandbar shows up. It's like tens of meters wide, hundreds of meters long, massive amount of sand that's self-organized. And so that was like really clear. Okay, this is the project. We got to understand, how do islands and sandbars form? Could we promote them to form? Um, it became clear that we were trying to address sea level rise and storm inundation or erosion. And there's really only two things that island nations and coastal regions do. Number one, they build walls, so they fight the forces of nature, and that never works. Nature always wins, or sometimes even worse, it amplifies the negative effects. So there's a lot of examples where the Army Corps of Engineers got sued because they put in a wall and it made the erosion worse, for example. So we know that that doesn't work. And the second one is dredging. Almost every beach around the world uses dredging. Also doesn't work. So you pump sand back onto the beach. They spend tens of millions of dollars. The sand washes away the next season or the next big storm, but it also destroys the reef, kills the marine habitat. So also doesn't work. Those are the only two things that people do. And so we were interested in, how do we find another alternative? In the Maldives, they do the same thing. So they dredge islands. They can build a new island in about a month. So it's all based on tourism, which is really not great. But we became interested in the same amount of time that it took them to build that island. These three sandbars built themselves. And the bottom one is the one I showed you before. So this is Skindy from the lab. He used to co-direct the lab. He now runs RLP, Liquid Printing Company. So when we arrived to the island, this is literally that moment. And it's over a meter above sea level. Like it's a massive amount of sand that these islands self-organized. And so that became clearly the goal. How do we promote that to happen? We try to study that for years and years and years to understand, like, why does sediment move and how does it erode and when does it accrete? Basically, the hypothesis became it's the relationship between the bathymetry, so the underwater landscape, and the force of the water. So currents, waves, and tides interact with the landscape underwater to either accrete or erode sand. So then the question was like, well, how do we change the landscape? What if we placed submersible structures underwater? Could we promote accretion back onto the beach? And so we do that by studying it computationally, so we can try to understand what the physics is and try to then study sediment transport and geometrically or kind of digitally place objects and then see how the sand would accumulate based on those objects. And then we do it physically. And Farida leads a lot of these experiments, and we put tanks and we pump waves or we flow currents or we change tide and we place objects, and then we see how does the sand accumulate or not based on those objects. So we try to understand the actual physics rather than simulating it. Even though the scale factor is not accurate, can we try to promote sand accumulation with those geometries? This is another tank where we have 8 pumps. We can turn on and off the pumps, and then the sand self-organizes in the middle. So these patterns emerge on their own. And this one led to a lot of satellite work that Walt Zesk, who's a PhD, he's finishing right now, and his dissertation is on satellite analysis. So basically, we started imaging this and try to then build a model that learns how to predict how the sand self-organizes from running this. And then we use that to translate it to satellite images. So we take satellite images and then we try to build a model that learns and predicts how coastlines are changing. So that's all the like tank experiments, but most of our work is in the Maldives doing field experiments. So we've done 10 of them. This slide's a little outdated. I'll show you a couple of the highlights. So recently, or originally it was National Geographic, then it was USAID funded, then that got killed, it got doged, which is unfortunate. But we got our projects finished, luckily, right before that. So this is a 90-meter structure. Those are people swimming. And these are actually like the ambassador to the Maldives and all the like government officials that came in suits and then they wanted to get in. And so we placed this structure, and it's an omnidirectional structure. And it's exactly what you saw in that purple and yellow simulation image. So we found what we thought was the optimal configuration for many different seasons for the sand to always accumulate in the same area. So it sort of like ratchets up. This was after one season. So we got 2 meters of new elevation change. This is in 5 months, and now it's been longer than that. But this is 2 meters of depth change. So now this is like someone's ankles walking there. We created this sandbar. Here you can see walking on top of it. Each one of those structures was 2 meters tall by 20 meters long. And we've now gotten over 800 cubic meters. This is a little outdated, but 800 cubic meters, and the sand is on top of the structures on the right. So it's covering all the structures over there. So anyway, over the years, these will continue to accumulate and grow more and more sand in this island configuration. We did another one, which was a quickly deployable. So this was in 40 meters in an hour. So lightweight, low cost structures. You can put them out with an amphibious excavator, and you can place these structures, and then the next season move them to the other side of the island, or move the configuration, change the orientation. Then we started looking at mangroves and natural systems. And so the vision of this one was, what if the sand accumulates from the bottom, but the roots grow down from the top, and the two could meet one another? And so the vegetation could stabilize the sand, it would trap more sand, and we could have a kind of natural, artificial interaction there. And so we made these floating gardens where you see each one of these things floats, and they had like native screw pine and mangroves and other species. And so the idea is they would float down as the sand was growing up, and they create this kind of marine habitat underneath. And so this is also the first time that we started thinking about this not as just infrastructure. Like, yes, it is infrastructure, but it also is trying to create a positive impact for the marine habitat and grow different algae, or grow a different coral, soft coral, hard coral, sea anemones. And then this one is one of the latest ones is at the JW Marriott. So we made 54 of these structures where we cast them directly into the beach. So we dug a hole in the beach, we cast a structure in, we pulled them out of the sand, and then we placed them in the water. And so there's 54 placed, and then they truly create a reef. So each one of these, it's got sand on it, all the calcium carbonate from the local environment. They start to grow coral. So this was after 6 months. There's just thousands of these natural coral recruits on it. It creates that habitat for the fish. It becomes a dive site for the guests. So we were thinking about the multiple constituents. Like, yes, it's infrastructure. It's all about rebuilding the beach and growing islands, but it's also about the marine habitat, and then it's also about the human experience. Like, think about Christo for the oceans, or can you think about some like big design artistic intervention that is in itself an attraction, in itself a positive for the community, or for the guest, or for the locals. And so we want like the human, the marine, and the coastal all to be. But the most important is that we grew 30 meters or 98 feet of beach in 6 months. And so just by placing the structure, we could see a pretty dramatic impact in how the beach grew, just by placing a passive structure. So anyway, all of that is ongoing in the Maldives. The vision is, how do we build with the forces of nature rather than try to fight them? Can we build with them? Can we utilize them as constructive forces? And then most recently that moved to Iceland, and we work now with volcanoes, kind of similar ethos, but we want to guide lava to then build with it, or to move it away from power plants or cities. And so we're trying to basically like harness the temperature and the power, the force of the lava. So this is becoming a much larger part of our work in like geological processes, or geological self-organization, and guiding the forces of nature. So how all of this stuff comes together, this to me is the state of the art. This is like every industry, cars, planes, shoes, houses, whatever it is. Everyone's like, I want smart cars, smart homes, smart whatever. And that means put a bunch of stuff in, put a bunch of motors, put a bunch of robots, put a bunch of sensors, electronics. It means the cost goes up. It means the failure rate goes up. It means the energy consumption goes up. It means the smart thing is dumb, and then the dumb thing is smart. Like, you get to this point where you have an inflection, like your Nest thermostat will work for like 1/100th of the amount of time that an old school thermostat will work for. So we're up against this weird conundrum where the more you try to make something smart, the worse it gets. And we're always up against that. Like, my lab is always trying to think about that. What's the most elegant solution to make the most intelligent intervention? And there's two visions. The left side says robotics. You can't see it, but there's two visions. So one is that there'll be more and more robots. Like, they aren't going away. Sergio wins. There's going to be robots everywhere. Robots are everything. But even if that's true, we still need smarter materials. We still need to be able to tap into the materials around us, and they are really great at physics. And so we need to be able to tap into them. The more ambitious one, though, going all the way back to the Big Hero 6 and the programmable matter, if you look at all the researchers that were under that DARPA programmable matter grant 20 years ago, almost none of them are working on robotics anymore. So almost every one of those researchers is working on programmable materials, soft robotics, let's see, soft GUI bio, granular jamming, textiles. Like everyone has moved to soft systems away from electromechanical systems. And I think that's because there's more and more evidence that materials, including ourselves, can have intelligence, can have an embedded logic, can be sensing, can be actuation. They can have all the things that robots have, but they're soft, they're flexible, they're agile, they're cheap, they're abundant, they're repairable. They're adaptable. So there's a lot of advantages. So the future of robots is moving to softer materials. So this is the vision of the lab. Today we built smart robots and machines, and tomorrow we'll build smarter materials and environments. So thank you so much. What time are we? Oh, 5 minutes?
5 minutes.
Yeah.
Oh,
Then I run.
Thank you
Yeah.
very much. Maybe we see if the students have questions.
Quick burning questions.
No. Yeah.
I mean, it is incredible. Yeah, please.
Looked at things in space as well, and like this kind of adventures as well.
Space meaning like outer space? Yeah. Yes, a little bit. So very early on, I did a proposal for NASA with Jeff Hoffman, who's a 5-time astronaut. And my proposal was let's use self-assembly in space. It was before we had done any of the Maldives stuff, and it was kind of naive. It was like early days of like, well, self-assembly is good in places where it's hard to build in traditional ways. So construction sites are not a great application, factories aren't a great application, but outer space is a good application, or like disaster relief or war zones or underwater or like high altitude or extreme temperatures, like all these places where it's hard to build. So we applied for that. We didn't end up getting it. But then 3 years ago, Jeff Hoffman and I and David Newman and Nicholas DeMancho started teaching the studio on space architecture. And then several years before that, David and I started collaborating on a spacesuit. So slowly we've been getting more and more into space environment. But do you know Ariel Akbal? Have you heard of her? She has a company called Aurelia Institute, and she literally does like what I showed, self-assembly for space. And so she has talked about like she was in Design Across Scales in Neri Oxman's version of it in the first year. And I presented the self-assembly stuff, and then she ended up like taking that, and now she has a whole company around self-assembly for space. So yes, they're doing that. I'm not doing it, but she's doing that. And it's like this dodecahedron that comes together and yeah, you've probably seen a video of it. She just presented at TED like last year or something. So yes, people are looking at that. Yeah, we're working on that in a way. Like we were teaching space architecture studios. We did it 3 years in a row. It's not our core research and we don't have funding for that. And to be honest, it's not really my passion. Like I would much rather be working on oceans and islands than space, but it's a really good example of a place that is hard to build. So it makes a lot of sense. Yeah. Other questions? Yeah.
So would you say that like whether or not the nature is like better at like creating solutions to these than like current solutions that people have done?
Yeah, I mean it's hard to say better. So I don't know who it is to quote on this, but I think many people have talked about that nature is not optimal. And nature is by no means like the best in many contexts. It evolves for very specific conditions in the evolutionary situation at the moment, which is maybe not exactly the same situation many years, millennia later. So the evolutionary decisions are not the optimal decisions, but they're the things that work enough, and then it moves on. So by definition, nature is not the best, but it's pretty damn good, and has evolved for many, many years. And so, I think it also the context of what we're designing, like if you want to design islands, it's much closer to like truly one-to-one, how do they naturally perform? So in that case, I think it's like very, very smart. I mean, it does this all over the world all the time, and we're all just trying to catch up to figure out how it does it. But if you want to say like, I don't know, the cheetah evolved this thing and now we want to translate it to this like super like spot robot, high tech, whatever. Well, the cheetah thing may or may not relate to your spot robot thing. Like, you know what I mean? Sometimes I feel like we force these and we're like, oh, nature did it, so let's just copy it. And it's like totally different context, totally different forces, different scales, different materials, different everything. So I think that's where like biomimicry gets into a dogma. It gets into like nature is good. So therefore everything that I say looks like nature is good. Like I'll make my robot look like a cheetah, so then it's good. You know, and you're like, robot has nothing to do with the cheetah just because it looks like a cheetah. So there's a lot of that that I'm like kind of allergic to, that like if it's looks like biology, then it somehow is like we all should bow down to it or something. But I also want to expand it before beyond biomimicry, because like there's a lot of systems in nature that are not biological that are genius, like minerals and like mountain formations and volcanoes and like all these like physics to me is a lot closer to natural systems than like some very specific thing in biology. So anyway, like yes, there's many cases where I think natural systems are like amazingly good at things, but there we also have a role as humans, and computation also has a role in analysis. And so, you know, I think you just need to be smart about like when do you listen to it and when do you be like, actually, that's not the right context, but why don't we like translate it into some new way? Yeah.
Can I ask one
Yeah.
question?
Yeah.
Pulling it back into the class a little bit and having designed a lot of the right? It's shown us a huge breadth of work of all the scales, but everything,
Yeah.
please note all the scales.
I didn't show nano, so maybe I didn't go small enough. Yeah.
You had 10 more.
Yeah.
But everything is very clear, right?
Yeah.
And you bring it back to the vision of the lab,
Yeah.
everything is very aligned. And my question is, what are those aha moments for you in which you've learned how to really edit or navigate to find what is your vision of the work, right?
Yeah, I mean,
Does that
there
make
could have been
sense?
1,000 other projects that I showed, and so part of it is like storytelling, and there's a million projects that maybe not a million, but there's a lot of projects that I'll never show, that we don't show or I don't talk about. There's a lot of projects that I do talk about, but I chose not to today, also like timing wise, or just like trying to tell a more coherent story. So there's a lot of work of how do you tell the story and what is the story, and that story of emerges and evolves over time. Like when I started the 4D printing stuff, I never like that probably wouldn't have been the vision, or like I wouldn't have imagined the multi stuff. So the story has to evolve, and now it has turned much more to like environments. And so like some parts of the story were there. So anyway, part of it is storytelling. And then part of it, I think, is just like self-critique and evolving as a person or as like a group, and thinking about like, well, you know, the robots and the programmable matter, center bits and atoms robot was like, okay, cool. That's not the future. That's not like we can do better. And then you do another one, and then you're like, that's not it. That's not it either. We can do better than that. And so each project is like either self-critiquing or being like, okay, cool, but what about if we did this? Like you kind of think about it as another direction, and just always using that as a driver for the next projects, the next opportunities that come. And I think that helps you refine, like, this doesn't feel like us. This doesn't feel like great work, but that didn't hit it, you know? And then there's some that was like, that's it. That's the thing. Like this is, and I think the Maldives one, you know, that we just got lucky that fell in our hands and like truly has become like a life project. And it's just like brings all the things that I care about or I believe in. Is like, okay, this is like the best example of what we can imagine. The most important project problem we could address, the global scale of it, like aligned with the vision and the whatever, like, you know, so, but some of that's luck, some of that is like opportunistic, some of that is self-critique and being like, you know, self-assembly stuff for 15 years didn't really fit. Like it was cool, but who cares? Like cool, you did a chair underwater. Who cares? Cool, you did balloons up in the air. Who cares? Like it's like magic tricks, but it's not meaningful. You know what I mean? And so a lot of that is thinking through like it's close, but it's not there yet. It's and then constantly like reevaluating it. And I think the 4D printing or a lot of those is similar. It's like cool, but not super useful. And then like slowly it's like, okay, if once we get into textiles, like, okay, now we're getting somewhere because everyone around here is wearing textiles. Textiles are everywhere in our world, homes and cars and planes and clothing. And so like if you can make an impact there, that's a big impact. So anyway, it's like evolving, self-critiquing. Yeah. Yeah.
I think it's incredible, Skylar, to also hear the essence of experimentations and iteration, which we talked about. I mean, we are in design across the scales and disciplines. So part of this is like actually doing things that maybe initially you feel like maybe it doesn't make sense fully. But then kind of finding yourself in this process and then iterating, and then something will emerge out of that as well. It's so wonderful. I want to thank Skylar for such an inspiring lecture. Every time I listen to you, I feel like, I heard something new.
Yeah.
So
That's good because you've seen it a lot. You've heard the presentation.
So help me
I do.
thanking Skylar.
Yeah.